All right, just take a look around you right now. In your home, at the office, wherever you are, you've probably got a laptop, a phone, a smart TV, maybe a dozen other things all connected to the internet. And they're all funneling through what looks like just one single connection. It really does feel like magic, right? But it's not. It's actually one of the cleverest, most important bits of engineering that holds our modern internet together.
So, have you ever actually stopped to wonder, how does that work? I mean, think about it. You've got Netflix streaming, you're on a video call, your phone is getting notifications. How does all that data go out and come back through one single address and not turn into a complete mess? Well, that's exactly what we're going to dig into. So, here's the plan. We'll kick things off with a crisis that nearly killed the internet in its cradle. Then, we'll look at the genius fix that came to the rescue, break down how it ticks, see what makes it scale up, and finally, check out the difference between the theory and what really happens out in the wild. All right, let's get right into it. To really get why the solution is so brilliant, you first have to understand the problem it was trying to solve. And back in the early days of the internet, there was a huge problem brewing. We were about to run out of internet. So the original system, what we call IPv4, had roughly 4.3 billion unique addresses. Now, that sounds like a ton, right? And for a while it was. But then came the 90s, and suddenly everyone was getting online. It became crystal clear very fast that 4.3 billion wasn't going to be nearly enough. We were speeding towards a cliff. So, the engineers in 1994 got together and came up with what they literally called a short-term solution. Just a Band-Aid, right? Something to buy them some time. But here's the crazy part. That temporary fix is still with us today, and has become one of the absolute cornerstones of how the internet functions.
And that solution is network address translation, or as you'll hear it, NAT. You can think of it as the unsung hero that lets your whole private network, all your devices, talk to the rest of the world.
So what is it? Well, at its heart, NAT is a service. It's usually running on your home router, and it's basically a master translator. It takes all the private internal addresses from your devices, the ones that can't actually go out on the public internet, and it rewrites the data packets so they all look like they came from the one public IP address your internet provider gave you.
And this right here is the whole idea in a nutshell. Think about it. Your home network, my home network, the coffee shop down the street, we can all reuse the same block of private addresses. You've probably seen them, the 192.168.1.something addresses. Because we can all do that, we don't need a unique, public, globally recognized address for every single phone, laptop, and smart fridge on the planet. And that was the key. That's how we conserve those precious few public IPs. And you know what? The benefits didn't stop at just saving addresses. Not by a long shot. NAT also gave us a nice built-in security boost by basically hiding your internal network from the outside world. It made setting up a local network way simpler. And get this, it meant you could change your internet provider without having to go and manually reconfigure every single device you own. I mean, it was a massive win all around.
Okay, so let's get into the nitty-gritty. How does this translation actually work? Well, it breaks down into two main flavors, and it all depends on which direction the data is moving.
The best way to think about this is to imagine your router is like the receptionist for a big office building. So when you send a request out to the internet, that's called source NAT, or SNAT. It's like you're handing a letter to the receptionist. They take it, cross out your desk number, put the building's main street address on it, and mail it. Now when traffic comes in from the internet, that's destination NAT, or DNAT. This is like someone calling the main office number. The receptionist answers, figures out who the call is for, say your web server or a security camera, and forwards the call to the right internal extension. Simple as that.
And here's what that looks like under the hood, without the friendly analogy. Yeah, I know, these diagrams can look a little complicated, but it's showing the exact same thing we just talked about. On the left with SNAT, you can see the source address getting rewritten from the internal one to the public one. And on the right with DNAT, the destination address gets changed from the public one back to the internal server. It's literally just the receptionist doing their job, but in packet form.
Okay, but wait a minute. This raises a really big question, right? SNAT explains how one device gets out. But how do your laptop, your phone, and your TV all use the same public address at the same time without all their data getting jumbled up into a big mess? Well, for that, we need another layer to this trick.
Yeah, this really is the million-dollar question. A packet comes back from Netflix. How in the world does your router know if that packet is for your smart TV or for your phone, which is also on the network? I mean, from the outside, they both have the exact same public IP address.
The answer, and this is the real secret sauce, is something called Port Address Translation, or PAT. This is the heavy lifter in your home router. It doesn't just change the IP address, it also uses port numbers. Think of it like this. Your public IP is your building street address. The port number is your specific apartment number. Every single connection that goes out gets its own unique apartment number.
And this is how it keeps track of everything. It's just a simple table, kind of like a little notepad. Your router keeps a list just like this one. So when your laptop asks for something from Google using, say, port 48635, the router jots it down. Then your phone talks to Netflix on a totally different port, 5603, and the router makes a note of that too. So when the replies come back to the building, addressed to those specific apartment numbers, ports, the router just checks its list and says, that one goes to the laptop, and this one goes to the phone. Easy. Problem solved.
So, this system seems incredible, right? You've got tens of thousands of ports available. It feels like you could have an almost unlimited number of connections, but are there any limits in the real world? Does it ever break?
Well, in theory, the numbers are just mind-boggling. I saw a network engineer on Reddit break this down once. When a router is tracking the full conversation, not just the port, but the source and destination IPs, the source and destination ports, and the protocol, the math just goes crazy. We're talking about a theoretical limit of hundreds of millions of connections. Yeah, let that sink in. Over 655 million. So the technology of NAT itself, that's not the problem. That's not the bottleneck. In theory, you could hide a massive city's worth of users behind just one public IP address.
So that leads to the obvious question, right? If the tech is that powerful, why do big networks, think universities, huge corporations, why do they sometimes run into issues with NAT? And this is where the perfect theory crashes into messy reality. The real limits aren't about the router, they're about how the rest of the internet reacts to you. First, there's a weird problem called port exhaustion, but it's not what you think. It's not running out of ports in general. It's running out of ports going to the same destination. So picture a university. Thousands of students all try to log into the same online exam site at 9 a.m. sharp. Bam! They can actually burn through all the available ports for that one specific connection. Then there are the other problems. If a service like Google sees a ridiculous amount of traffic coming from your single IP, their systems are going to think something's up. They might slow you down, block you, or make you click on 1,000 pictures of traffic lights to prove you're human. So when you boil it all down, the limit isn't technical. It's almost social. It's a security thing. The rest of the internet is just not set up to trust one single address that's behaving like an entire city. The real challenge is just trying to fly under the radar.
And that kind of brings us full circle, doesn't it? NAT was supposed to be a short-term solution back in 1994, and here we are, decades later, and it's completely shaped the internet as we know it. But now there's IPv6, the successor that has a practically infinite supply of addresses. It's slowly rolling out, and it promises to bring back that original vision of the internet where every device has its own unique address. So you have to wonder, is this clever little trick that saved the day, finally, after all this time, about to become obsolete? That's the big debate happening right now.